So let's consider the following linear program. This program is very similar to previous ones. It's just that now the right hand side is 6 and 8 to make our calculations easier. So with this particular solution, the standard form would be adding x3 and x4 to make them equalities. So this should be fine. And now we know we need to keep track of the objective value, because whenever we say we improve, that means our objective value is increased or decreased according to the objective function. So we want to keep improving. So let's say we use z to be 2x1 plus 3x2 to denote our objective value. And because this is so common, sometimes we just call it the z value in the field of operations research. So when we talk about linear programming, integer programming, whatever, the z value is typically used to denote the objective value. Okay, so one thing we want to do is that we want to keep track of this z value. And we know we are maximizing z. And also all other variables except z must be non-negative. So maybe we may say that as long as we know these two things by ourselves, all the remaining things may be expressed in these three equations. Okay, here we have three equations. Previously we have two that are about constraints. We now express the objective function as a third equation. So it's here. Pretty much the last two are the constraints. Okay, so they are nothing different. They are nothing special. We simply add the first one, z minus 2x1 minus 3x2 equals 0. This is going to be, again, another equation that must be satisfied throughout the whole process. Whatever x1 and x2 you have, somehow the z value must satisfy this equality. Okay, so that makes sense. So pretty much what we are doing is to take the objective function and express it as an equality. So this constraint, which is not really a constraint, which is actually an objective function, this constraint would be called the zeros constraint throughout the process. So what we will do is to take a look at this system of three equations and keep modifying the values for x so that we may find feasible solutions with higher values of z. So let's start. To start the search process, we need to first have an initial basic feasible solution. So in general, an LP is solved with two stages. In the first stage, we will search for an initial basic feasible solution. Somehow we need to find a way to do this. Okay? Let's assume we already have an initial basic feasible solution. Then in the next stage, we will keep moving along edges until we find an optimal basic feasible solution. Okay? So somehow we will first focus on the second stage. Let's assume we already have an initial basic feasible solution. Let's tell you how to find an optimal one. Then at the end for today's lecture, we will tell you how to find an initial one. Okay? So we need to somehow first have an initial basic feasible solution. Luckily for this particular example, this is very easy. If we look at this system again, all we need to do is to select two columns, right? We want to select two columns to make this system solvable. How about this? Let's select x3 and x4. If we say x3 and x4 are the set of basic variables, then all we need to do is to say, hey, x3 is 6, x4 is 8, and then we're done. This is indeed feasible. So this is a situation that selecting x3 and x4 definitely works. Because what? Because of what? Because for the two columns, they form an identity matrix. So when we want to solve AB xB equals small b, that just means I xB equals small b. And then xb equals small b. And also, you know small b is non-negative according to the definition for standard form. So that's why your xb is also non-negative and is a basic feasible solution. It's not the case that you always have an identity matrix here for free. It is because that here, the two constraints originally are less than or equal to. So you add slack variables for each constraint, and then you get this identity matrix. Okay, so we have this by chance. Later, we will show you how to deal with other cases in finding a basic feasible solution initially. But here, let's take it as given and see what should we do. So now we're going to start from our basic feasible solution, the initial one, from 0068. So these two variables, x1 and x2, they are non-basic, so they are 0. x3 and x4, they are basic, so that's positive, 6 and 8. The current basic feasible solution gives us the objective value, which is 0. Why is that? Because if you plug in this solution to your objective row, you do see that your z is 0. Okay, so I hope that makes sense. So somehow we now want to move to our adjacent basic feasible solution. That means we need to select either x1 or x2 to enter the basis. So which one should we do? Well, the zeroth row or the zeroth constraint is going to give us some hint. Okay, so there's no s here. Okay, so the hint is that we may look at their coefficients so that we know what's the impact of increasing that particular variable to on z. So you do see this -2 here. What does that mean? That means if your x2 is increased by 1, your z must be increased by 2 so that the equality still holds. Similarly, if you see this -3, you understand that if you increase x2 by 1, you are going to increase z by 3 so that the equality still holds. Somehow that means, oh, that's good, because increasing x1 or x2, both would increase our value for z. And this is a maximization problem. So we want z to be as large as possible. So choosing x1 or x2, both would increase our objective value z. But of course, we need to somehow pick one. So let's assume we will choose x1 to enter. You may want to ask, what's the point of not choosing x2, right? Because choosing x2 seems to be better. But very quickly, we will show you why it is not always the case. All right, so if we want to increase increase x1, let's see what's going to happen. And let's see how to select a living variable. So now x1 goes up from 0. So if x1 goes to 1, goes to 2, we need to keep an eye on the impact of the basic variables. Basic variables originally are 6 and 8. Once you increase x1 by 1, from the two equations, you may see that if x1 is increased by 1, your x3 must decrease by 1. That's why 6 becomes 5. And if x1 is increased by 1, x4 must be decreased by 2. So that's why your 8 becomes 6. So 0068 becomes 1056, becomes 2044, and so on and so on. Very quickly, you would see that our x2 remains 0 because we are not changing that basic variable, a non-basic variable. It remains 0. So very quickly, we will get to a point 4020 when x4 becomes 0. x4 becomes 0 before x3 becomes 0. So x4 hits 0 the first. That means our x4 should be the living variable. Okay, so previously our basis is x1 and x2. Our basis is x3 and x4. Okay, and we know x1 would enter, x4 would leave. What does that mean? Later we will change x4 to x1. And if you go back to see what we were trying to do, we first see which entering variable may benefit the objective function. And we see which basic variable hits 0 the first. That allows us to do all the checking, all the determinations. So for the leaving variable, actually determining which one would hit the 0 first is also very simple. All we need to do is to look at the ratio of the right-hand side values and the entering column. For this particular example, we focus on the coefficients for x1, okay? Because x1 enters, so this 1, 2 is the entering column. And the right-hand side, 6, 8. 6 divided by 1 is 1, okay? The 1 is here, which means you may increase x1 up to 6 before you may require x3 to become 0, okay? And 8 divided by 2 is 4. That means you may increase x1 up to 4 before you make x4 becoming 0. So this ratio directly tells us that the second ratio is smaller, 4 is less than 6. So x4, which corresponds to the second ratio, is going to hit 0 first. And that somehow tells us that, oh, okay, so x4 would be the leaving variable. So once we know, we will change from x3, x4 to x3, x1. We may resolve the whole system. Or if you keep an eye on what we are doing, we know we would stop at 4020. That's our x2. And now our z value would be increased to 8. That's indeed an improvement. So pretty much that's the idea we need to do with the simplex method. We take a look at the zeros row to see which non-basic variable should enter. And we do some kind of ratio test between the right-hand side column and the entering column to see which basic variable would hit 0 first. And then we are able to change to our new basis, and then we may do it again, and again.